Okay, so far we've looked at one-dimensional motion. So we went either left and right, but we also did up and down, including gravity. Now we're going to extend these ideas to 2 and 3 dimensions. So we can use vector notation to define a position and velocity. The position is given by the vector r. So the arrow above the r indicates it's a vector. So we have x in I hat direction plus a y component in the j hat direction and a z component in the k hat direction. So x, y, and z are the scalar components, and I, j, and k are the unit vectors that point in the x, y, and z directions. The displacement is still the final position minus the initial position. So in vector form, the displacement then becomes delta r, which is equal to r2 minus r1. So r2, we have x2 I hat plus y2 j hat plus z2 k hat, and then minus r1, which is x1 I hat plus y1 j hat plus z1 k hat. So we get displacement in x in I hat plus the y displacement j hat plus the z displacement k hat. Then we can write average velocity as displacement r over the time. So that's delta x over delta t I hat plus delta y over delta t j hat plus delta z over delta t k hat. Of course, delta x over delta t is the average velocity in x, and the delta y over delta t is the average velocity in y, and delta z over delta t is the average velocity in z. So we have v average x I hat plus v average y j hat plus v average z k hat. So the diagram to the right there, this is in the xy plane, and we have something moving in the xy plane. First we're at position 1, and then later we're at position 2. So this shows the vector position 1 r1 and vector position 2 r2, and then delta r is r2 minus I1, points directly from position 1 to position 2. To get the instantaneous velocity, we take the limit as delta t goes to 0, and then that gives us the derivative, dr dt. And dr dt we can write as dx dt I hat plus dy dt j hat plus dz dt k hat. So notice then that the velocity vector, we can just differentiate the scalar components of position with respect to time to get the scalar components of the velocity. The diagram, again, as the particle moves in the xy plane, we see then that the velocity vector is tangent to the path. So we have a path in the xy plane. The velocity will be tangent to the path. So the instantaneous velocity is the tangent at any point along the path. Now let's look at acceleration. Acceleration, of course, if we're in the average, we have v2 minus v1 over delta t, or delta v over delta t, and then if we take the limit as delta t goes to 0, we get the instantaneous acceleration, which is dv dt. So it's a derivative of the velocity with respect to time. So note that if the velocity changes in either magnitude or direction, the particle must have an acceleration. So even just changing direction of the velocity without changing the speed, just simply changing the direction, there's an acceleration because the velocity vector is still changing. Now also note that the acceleration vector does not necessarily extend from one position to another, and in fact it usually doesn't. So if we have the path drawn in the xy plane, the direction of the velocity will be tangent to the path, but the acceleration is not. The acceleration points in the direction that the velocity vector changes. So that's not going to extend from one position to another. Now another thing to notice, the acceleration, we have an x component in I, a y component in j, and a z component in k. So if one or more of the scalar components of the acceleration are zero, then the velocity component in that direction does not change. So, for example, if I only have acceleration in y, then the velocity in x or z does not change. That means dv dt is 0. Or dv dvx dt would be 0, and dvz dt would be 0. So if we only have acceleration in one direction, the velocities in the other directions do not change. So the acceleration in one direction only affects the velocity in that direction. It cannot change the velocities in other directions. That's a very important thing to keep in mind. Alright, so now we're going to look at the special case of 2D motion called projectile motion. So this is free fall motion with both x and y components. So some examples are hitting a golf ball, hitting or throwing a baseball, kicking or passing a football, etc. So the particle is launched with an initial velocity and is only under the influence of gravity after the initial launch. So since gravity only acts in the vertical direction, so our only acceleration is in the vertical direction, and it's down towards the center of the earth. Thus, the horizontal motion is constant, since acceleration in the vertical direction cannot affect the motion in the horizontal direction. So we can treat each motion separately, but realize that they both occur in the same time frame. So it's just like making a vector notation. So we have an x component and a y component. The y component has constant acceleration. The x component has 0 acceleration, so it will be constant velocity motion. So now our equations of motion become these. So in the horizontal direction, x is just x naught plus v0xt, where v0x is the x component of the initial velocity. The velocity then is constant. So the velocity at any later time will equal the initial velocity in the horizontal direction. The vertical direction is just our vertical free fall that we already learned. So y as a function of time is our initial y position plus the initial velocity in the y component times time minus 1/2 gt squared. And velocity then is v naught y minus gt. And then of course we always have the third equation where we eliminate time between the first two, and we get vy squared minus v naught y squared equals minus 2g delta y. So these are our kinematic equations now. So we can treat the horizontal motion and vertical motion separately, and then they occur in the same time frame, so then we can just make the horizontal component and vertical component the components of our vector. So if I give something with an initial velocity, I need to break that initial velocity vector into horizontal and vertical components. So again, we make the vector the hypotenuse of a right triangle, and then the vertical component and horizontal component are the legs of that right triangle. And so the v naught in the x direction is v naught cosine theta, and in the y direction is v naught sine theta, where theta is measured from the horizontal, just like in the diagram. So this gives us the initial velocity components in the horizontal or x direction and vertical y direction. Now again, remember, the horizontal and vertical motions are independent of each other. They occur in the same time frame, but one does not affect the other one. So neither motion affects the other. There is no acceleration in the horizontal direction. The acceleration is only in the vertical direction. Things do not fall sideways. So for projectile motion, note the acceleration vector only has a y component. So the acceleration vector is just minus g in the j direction. So the horizontal motion is constant velocity motion, and only the vertical motion has an acceleration, and it's g, the acceleration due to gravity. All right, here's an example problem. A ball rolls off a 2-meter high ledge with a velocity of 1.5 meters per second. A. How long does it take to hit the ground? B. What horizontal distance from the edge does it hit the ground? All right, so part A, how long does it take to hit the ground? Well, since it's rolling off the ledge, the initial velocity in the vertical direction will be 0. As it goes off the edge, it will only have a initial velocity horizontally. There's no initial velocity vertically. So the vertical motion is the same as if we just simply dropped it from a height of 2 meters. So since we know it falls 2 meters, and we can get the distance it falls, we can write as 1/2 gt squared. So we solve for t. So multiply both sides by 2, divide by g. We get t squared equals 2d over g, or t equals the square root of 2d over g. So the distance is at 2 meters, and the g is 9.8 meters per second squared. And so that gives us a time of 0.64 seconds. So that's how long it takes to fall to the ground. Now, we know it's going to be in the air for 0.64 seconds. So now we can get the horizontal motion. We know the initial velocity, so the velocity times time will give us the horizontal distance. So we know how long it takes to hit the ground, so we just find how far it travels horizontally in that time, and the horizontal motion is just the velocity times time. So we get 1.5 meters per second times the 0.64 seconds, and it gives us 0.96 meters. So that's how far it travels horizontally as it falls. All right, here's a check your understanding question. 2 metal balls are the same size, but one weighs twice as much as the other. The 2 balls roll off the edge of a horizontal table with the same speed. So in this situation, A, the heavier ball hits the floor at about half the horizontal distance from the base of the table than the lighter ball. B, the lighter ball hits the floor at about half the horizontal distance from the base of the table than the heavier ball. Or C, the heavier ball hits the floor considerably closer to the base of the table, but not necessarily half. D, the lighter ball hits the floor considerably closer to the base of the table than the heavier one, but not necessarily half. Or E, both balls hit the floor at approximately the same horizontal distance from the base of the table. So you should be able to answer this one. Think carefully. The answer, of course, is E. Both balls hit the floor at approximately the same horizontal distance from the base of the table. Well, why is that? Well, it's because they both roll off the table at the same speed. It doesn't matter that one is heavier than the other. Galileo proved that a heavy object and a light object both fall to the ground at the same time, regardless of how much they weigh. So it doesn't matter how much they weigh. They both fall at the same rate. And since they're both traveling horizontally at the same speed, they both fall to the ground at the same time, and they both travel the same horizontal distance as they fall. So it doesn't matter how much they weigh. So very, very important to remember that. Everything falls to the ground at the same rate. It doesn't matter what their mass is. And since their horizontal motions have the same velocity, they will travel the same horizontal distance as they fall. All right, we'll take a break here. And in the next video, we'll do some more examples of two-dimensional projectile motion. So you should try to work some problems yourself. Now that you have some basic understanding of 2D projectile motion, try to work some problems yourself before watching the next video. But if you're ready to go on, well then just click on the links here.